Hello everybody. My name is Ricardo Grando, and I'm going to present the work Mapless navigation of a hybrid air and air vehicle with reinforcement learning through environmental generalization. It's a work of Federal University of Rio Grande in the context of Hydron, the project Hydron. Previous works showed that deep reinforcement learning can be applied to perform Mapless navigation of this kind of vehicle. Not only the navigation, but also the medium transition problem. So in this work, we address these two problems and we use two novel state-of-art actor algorithms for this case. So we showed that our novel algorithms that take into account double critic architecture, novel architecture of deep reinforcement learning, and also recurrent neural networks. This approach improves the navigation performance of this kind of vehicle, taking into account only range data and relative localization, a simple kind of sensing for this kind of robot. So our approaches achieve better navigation and transition capabilities, and also solid generalization of learning through distinct simulated scenarios that we use, and outperforming previous approaches for this case. So in our methodology, we developed two new algorithms, a deterministic one and a stochastic one. Both algorithms were based on existent algorithms in the state-of-art algorithms. The deterministic algorithm was based on the delayed policy gradients to the tree, and the stochastic algorithm was based on soft actor grid. We inserted two characteristics in these algorithms. First was the use of the double critic. So we use two neural networks for the critic agent that improves the learning and avoid the agent to get fitted to some kind of specific of learning. And we also insert the delayed policy updates that makes the agent also learn slow, but avoid to get into a place where he simply stops learning or does not learn a sufficient amount of information from the environment to perform the tasks. We use a sensing based on the real world sensors for the aerial navigation, the aerial part of the vehicle. We use a LiDAR, and for the radar simulation, we use a sonar. So in the air, we use 20 samples from this LiDAR, simulated LiDAR. We get the samples equally spaced in 13.5 degrees of this LiDAR that has 270 degrees. And the radar, we get information from a simulated sonar from a software developed, a plugin developed for the gazebo simulator. We got 20 beams as well, 20 samples, 20 beams from this sonar. We get that equally spaced of the total amount of beams that it is 256, and we get the highest beam of each beam, so that gives us the position of the obstacle for each beam. So the structure of our neural network, it has 26 samples, 26 observations, 20 from the sensing, like I said. We also use the three information from the past actions, which are the relative position to the target goal, and also we use the relative angles for the goal as well. Two angles. First, in the relative to the target x and y plane, and also another angle to the z distance plane. So we get these two angles, two relative angles, and use these angles as information as well for the agent. That improved a lot the learning of our agents, both deterministic and stochastic. So we have 26 inputs basically, an observation of 26 samples, and on the exit of our neural network, the actions are basically the linear velocity, the altitude velocity, and also the variation of the angle, the variation of the vehicle angle. We used 500 steps of training the steps of training for each episode. It was generated in a random manner um, to increase the generalization, the learning of the agent. We trained for 1,500 episodes in total for each agent that we used. The rewarding system is very simple. If a positive reward is given if the agent achieves the target, the goal, and the negative reward is given if the agent just collides some obstacle or with the scenario that he is performing. The results, our approach performed slightly better than previous approaches in state of art. Mainly in the second, more complex environment. So the first environment was a simple environment with just 4 obstacles. In the second environment, we used much more obstacles in a random manner to make it more complex for the agents. We tested with 100 trials of navigation for each one of the approaches that we developed, and also for each one of the approaches that we used compared to. So overall, our agents performed slightly better, especially in the second scenario with better navigation and a better capacity to avoid collisions. Here we can see a few samples from the navigation used in the first scenario that has just a few obstacles, like driving hazards, for example. The main contribution of our work is on the generalization, is on the idea of generalization that we did in the second environment. So we did another test, another evaluation. Basically, we trained, we get our models that we trained in the first environment and tested on second environment. So these models didn't know anything about the second environment, so they were tested, evaluated in the second environment. That's was one of the ways that we evaluated. We also get these agents trained in the first environment and trained for a few more on 100 episodes in the second environment. So we had an agent that was trained in both environments, and then we evaluated in the second environment. And also we did a third final evaluation that was just evaluating the models in the second environment and tested in this same environment. Overall, we can see that the agents that was trained in the first environment performed much better than we expected in the second environment, even though they didn't have any information about this environment. And when we just trained for a couple more episodes in the second environment, we got very good results, especially our stochastic approach that achieved a performance of 83 trials of success in total of 100 trials. So it was a good performance. Here you can see very fast our robots navigating in the third scenario, which is a more complex scenario like you can see. So he's navigating in the center of the scenario to a target goal in the underwater. In the right here, you can see the information from the sonar, visualization of sonar. That was a sample of navigation from air to water, and also did a navigation from water to air as well. So conclusion in future works, our approaches were capable to present a consistent performance, especially in the air to water navigation. They learned they showed an ability to learn the tasks and the environmental difficulties, not only the scenario. So we can conclude that our double critic approaches with this kind of RNN in a LSTM network presented a better ability to learn through distinct scenarios. It's also important to mention that these approaches were extensively evaluated in realistic simulation, including control issues and disturbance like the wind, for example. So that's it. Thank you for your attention.